65 meters. That is the height of a 20-story building. Now imagine you have to lift a fully loaded cargo ship 5,000 tons of steel, coal, and raw materials over that building. Not once, 3 times, across 134 kilometers of mountains, rivers, valleys, and living ecosystems. And someone decided to do exactly that, right here, in southern China. Welcome back to the channel. What you are about to witness is one of the most audacious feats of civil engineering ever attempted in the 21st century. A project so massive in its ambition, so extreme in its execution, that engineers had to move nearly 3 times more earth than the entire Three Gorges Dam just to carve the path. This is the Pinglu Canal, and it is unlike anything built on this planet in the last 70 years. This is not just a canal. It is not a trench dug between 2 rivers. It is a complete rewriting of geography, a 134.2-kilometer artificial waterway slicing through the mountainous heart of Guangxi province, connecting the inland river networks of southwest China, rivers that have flowed east for millennia, to the open waters of the Beibu Gulf and the South China Sea. It is China's first river-to-sea canal since the founding of the People's Republic, the first one in over 70 years. And when it opens, it will not simply move cargo faster, it will reshape the economic destiny of an entire region and send ripples across the trade routes of Southeast Asia. Now, before we go any further, imagine you are standing on the banks of the Xi River in Nanning, the capital of Guangxi. Around you, barges and cargo vessels sit low in the water, loaded with coal, bauxite, agricultural goods, steel, fertilizer, the lifeblood of an inland economy. These ships need to reach the sea. They need to reach Vietnam, Malaysia, Indonesia, the ports of Southeast Asia. But look at the map. The sea is close. Qinzhou, a major port city on the Beibu Gulf, is barely 130 kilometers away in a straight line. And yet, those ships cannot get there. Not directly, not by water. Because between them and the sea stand mountains. And the rivers, by some cruel accident of geology, flow in the wrong direction. Before we continue, make sure to subscribe to the channel and hit the notification bell so you never miss a video. We cover the world's most extraordinary engineering projects, the ones that change how humanity moves, builds, and lives. And stay with us until the end of this video, because what those ships will be sailing through, the locks, the hidden infrastructure, the ecological systems buried beneath the waterline, is even more extraordinary than the canal itself. So, let us begin at the beginning. Let us begin with what was here before. At first there was only landscape, no waterway, no locks, no bridges, no navigation hubs. Just the rolling red-earthed hills of Guangxi dense with subtropical vegetation, the Lingshan Basin, the Karst Mountains. The watershed divide, that silent geological boundary where rainwater decides whether to flow north and east toward the Pearl River system or south toward the Qin River and eventually the sea. This divide had existed for millions of years, and for centuries it had been the invisible wall separating the inland economy of southwest China from the ocean. The rivers of Guangxi are extraordinary. The Xi River and its tributaries, the Zhuojiang, the Yujiang, the Qingnian, the Hongshui form one of the largest inland waterway networks in China. These rivers reach deep into Yunnan, into Guizhou, into the resource-rich interior. Millions of tons of goods move along them every year. Coal from inland mines, bauxite from Guangxi's mountains. China holds some of the world's largest reserves. Agricultural products from Yunnan's fertile plateaus, raw materials for factories, finished goods from growing industrial zones, all of it riding the current of these rivers, moving east, always east, toward the Pearl River Delta, toward Guangzhou, toward the ports of Guangdong province. And that was the problem. Not just a logistical problem, a structural one baked into the geography of China for thousands of years. To understand it fully, picture a cargo ship leaving a port on the Xi River in Guangxi. It needs to reach Qinzhou right there on the Beibu Gulf, barely 130 kilometers to the south, but it cannot go south. The rivers don't go south. So it goes east instead, hundreds of kilometers east through the Pearl River system, all the way to Guangzhou and the Pearl River Delta. And from there it heads back west and south, crawling through congested shipping lanes past the megaports of Guangdong, before eventually reaching the Gulf of Tonkin. Total detour, More than 560 kilometers, more time, more fuel, more cost, more congestion, and more dependence on the ports and infrastructure of a neighboring province. For the inland provinces of southwest China, Guangxi, Yunnan, Guizhou, this was not a minor inconvenience, it was a structural economic disadvantage that had persisted for generations. These provinces are not poor in resources. Guangxi alone has massive deposits of bauxite, manganese, tin, and limestone. Yunnan has phosphate fertilizers, non-ferrous metals, and one of the most biodiverse agricultural bases in Asia. Guizhou has coal, rare earth materials, and a rapidly growing technology sector. But getting those resources to global markets, efficiently, cheaply, competitively, had always been harder than it needed to be. Cargo that should have taken days to reach Southeast Asian ports was taking weeks. Transport costs that should have been low were inflated by the detour through Guangdong, and the ports of Guangzhou and Shenzhen, already among the busiest in the world, were getting more congested every year. If you tried to fix this problem with roads, you ran into the mountains. If you tried to fix it with rail, you faced the elevation changes and the cost of tunneling. If you tried to fix it with the existing rivers, you hit the geological reality. The rivers simply do not connect to where you need them to go. There was no easy answer. There was only one answer. Build a canal, not a small irrigation canal, not a flood control channel, a full Class I inland waterway, the highest classification in China's system, capable of carrying 5,000-ton cargo vessels, a canal 134.2 kilometers long, a canal that would cross the watershed divide between the Sea River system and the Qin River, climbing and descending 65 meters of elevation in the process. A canal that would need to be carved through some of the most geologically complex terrain in southern China: karst limestone mountains, fractured rock formations, unstable soils, river crossings, wetlands, and agricultural land. A canal that would require the excavation of 315 million cubic meters of earth and rock, a number so staggering it is almost impossible to visualize. To put that in perspective, the Three Gorges Dam, the largest hydroelectric project ever built, the dam that reshaped the Yangtze River and displaced over 1 million people, required the excavation of approximately 102 million cubic meters of earth. The Pinglu Canal required 3 times that volume. Not 3 times the concrete, not 3 times the steel, 3 times the earth moved out of the ground, across 134 kilometers, by teams of workers, machines, and engineering systems working continuously season after season through subtropical heat and monsoon rains for years. This was not a project. This was a geological intervention. So how did they do it? It began, as all great engineering projects must, with a question of what exactly needed to be built, and the answer was more complex than any single structure. The Pinglu Canal is not one thing, it is a system. A living, multifunctional engineered ecosystem that combines navigation infrastructure, water management, flood control, irrigation, ecological preservation, and advanced digital monitoring into a single continuous corridor 134 kilometers long. The first task was understanding the terrain. Survey teams moved through Guangxi for years before a single shovel of earth was turned. Geologists mapped the karst formations, the porous limestone riddled with caves and sinkholes that makes construction in southern China uniquely dangerous. Hydrological engineers analyzed every river, every seasonal flood pattern, every watershed drainage characteristic along the proposed route. Environmental scientists assessed the biodiversity of the regions, the fish species, the migratory birds, the wetland ecosystems that had never been disturbed by industrial construction. Digital twin technology was deployed, a complete virtual replica of the project, built-in software before being built in the ground, allowing engineers to test every system, every load, every water flow scenario before committing to concrete and steel. The route itself was carefully chosen. The canal begins at the Pingtang River estuary of the Sijin Reservoir near Hangzhou in Nanning. From there it runs southward, cutting through hills, crossing rivers, navigating around protected zones, until it reaches the town of Luwu in Lingshan County. At that point, it joins the natural course of the Qin River, which carries it the final stretch into Qinzhou and the Beibu Gulf. The name Pinglu itself is a deliberate echo of this geography, a portmanteau of Pingtang and Luwu, the starting point and the joining point, the two ends of the human-made section of the journey. The critical technical challenge, the one that defines the entire engineering solution, is that watershed divide. The terrain between the Qishi River system and the Qingnian River is not flat, it rises. For a canal to function, water must flow. And for ships to move from an elevated inland river down to a sea-level port, or back up again, you need something that the ancient engineers of the Grand Canal understood 2,000 years ago and that modern engineers have refined into something extraordinary. You need ship locks. Not just any ship locks. Not the simple single-chamber locks you find on smaller waterways around the world. The Pinglu Canal requires 3 full cascade navigation hubs, Madao, Qishi, and Qingnian, each positioned at a critical elevation change along the route, each serving as a kind of mechanical mountain pass for ships. And each one of these hubs is, in its own right, one of the most sophisticated pieces of hydraulic engineering on Earth. But before those hubs could be built, the path itself had to be carved. Construction officially began on August 28, 2022. The groundbreaking ceremony in Guangxi marked the start of what would become one of the largest earth-moving operations in human history. Within months, the scale of the mobilization was extraordinary. At its peak, over 35,000 workers were active on the construction site simultaneously, spread across 134 kilometers of terrain, working in dozens of separate teams on excavation, foundation work, concrete pouring, bridge construction, and ecological management. The site was not one place, it was a corridor, a moving, evolving industrial frontier stretching across an entire region. The first major phase was channel excavation, and this is where those 315 million cubic meters of earth and rock enter the story. The Pinglu Canal is not carved through soft, uniform soil. The geology of Guangxi is notoriously complex. Much of the route passes through karst terrain, the same porous cave-riddled limestone that creates the dramatic peaks visible across southern China. Karst rock does not behave predictably. It has voids, it has underground water channels. When you excavate through it, you can encounter sudden voids, unexpected water inflow, unstable formations that collapse without warning. Engineers had to map the subsurface geology in extraordinary detail, adjusting blasting patterns, excavation sequences, and support structures in real time as they encountered new conditions underground. In the Lingshan section, where the canal crosses unstable alluvial soils rather than rock, the challenges were different but equally severe. The excavation created trenches between 5 and 11 meters deep. The surrounding soil, disturbed by the construction, became prone to waterlogging, the hydraulic conductivity of the ground reduced by up to 70% in some areas due to soil compaction from heavy machinery. During monsoon season, this section flooded repeatedly. Engineering teams had to develop dynamic dewatering systems, constantly pumping groundwater and surface runoff to maintain safe working conditions and prevent the excavated channel from filling with water before the lining could be installed. Then there was the watershed crossing, the most critical 6.5 kilometers of the entire route. This is the section where the canal crosses the drainage divide between the Qishi River Basin to the north and the Qingnian River Basin to the south. Here, engineers were not simply digging a channel, they were creating a passage through a hillside. The excavation in this section reached depths far beyond anything encountered along the rest of the route, requiring precision blasting in karst rock, intensive slope stabilization to prevent landslides on the cut faces, and meticulous management of the enormous volumes of excavated material that needed to be removed, managed, and in many cases repurposed. And that repurposing is one of the remarkable hidden stories of this project. Of the 315 million cubic meters of earth and rock excavated from the canal route, approximately 210 million cubic meters were not simply dumped, they were used. Transported to nearby valleys and low-lying areas, they were used for gully filling and land reclamation, a process that, when completed, will have created around 940 hectares of new arable land. In a region where flat agricultural land is scarce and precious, this transformation of construction waste into productive farmland is not an afterthought. It was a planned component of the project's ecological and social value from the beginning. Every cubic meter mattered, every mountain mattered, every valley mattered. As the main channel excavation advanced, kilometer by kilometer, section by section, a parallel construction process was underway at the 3 hub sites. Because while the channel is the body of the canal, the navigation hubs are its heart. Let us talk about Madao first. Of the three Cascade hubs, Madao is the most extreme. It sits near the southern end of the main excavated section, at a point where the terrain drops sharply. The elevation difference managed by the Madao locks alone is 30 meters, the equivalent of a 10-story building that ships must climb or descend to continue their journey. To accommodate this, engineers had to carve a valley between two mountains at this location, an excavation so deep and so wide that it essentially created a new geographical feature in the landscape. The lock chambers at Madao and at each of the three hubs are 300 meters long and 34 meters wide. To give you a sense of scale, that is long enough to hold 3 full soccer fields end to end and wide enough to comfortably fit a 4-lane highway. These are among the largest inland ship lock chambers built anywhere in the world. And the engineering inside them is even more remarkable than their size suggests. These are water-saving locks, not in a vague aspirational sense, but in a precise engineered sense. A conventional ship lock works by flooding the chamber from the upper level and draining it to the lower level each time a ship passes through. In a system as large as this, that process would consume enormous quantities of water. Water drained away from the river system every time a vessel changes elevation. On a busy commercial waterway, that water loss could be unsustainable. The engineer's solution was to design each lock hub with adjacent water conservation basins. When a lock chamber is drained, lowering a ship from an upper level to a lower one, instead of releasing all that water into the lower river, a portion of it is diverted into these storage basins. When the next ship needs to be raised, the stored water is fed back into the chamber first, before drawing from the upper river. The result? The Madao hub locks reduce water consumption by 63% compared to a conventional lock system of the same size. And across all three hubs, the water-saving impact is substantial enough to make the canal viable in a region where water resources must be carefully balanced against agricultural, municipal, and ecological demands. But size and efficiency alone are not what make these locks extraordinary. Speed matters too, because a canal's commercial value depends not just on how much it can carry, but on how fast ships can move through it. Slow locks create bottlenecks. Bottlenecks kill economic viability. The lock gates at the Qishi and Madao hubs take approximately 1 minute to open and just 30 seconds to close. At full operational capacity, the three hub complexes can accommodate 6 5,000-ton vessels per hour, 6 ships every hour. Moving through locks the height of apartment buildings, rising and falling through chambers the length of 3 football fields, controlled by gate systems that open in 60 seconds. These are described as the fastest operating water-saving ship locks in the world. And that description, in this case, is not marketing language, it is engineering specification. More than 10,000 temperature sensors were embedded into the concrete of the lock structures during construction, connected to an intelligent monitoring system that tracks thermal conditions in real time and adjusts curing processes to prevent cracking in the massive concrete pores. In a structure where a single concrete element might weigh thousands of tons, thermal management is not optional. It is the difference between a lock that lasts a century and one that fails in a decade. Then came the bridges. A canal 320 kilometers long does not exist in isolation. It crosses roads, it crosses other rivers, it crosses railways, farm tracks, irrigation channels, and the daily movement of hundreds of thousands of people who live along its route. Every crossing point requires a bridge, and the Pinglu Canal required 27 of them, newly built or substantially reconstructed, ranging from modest local road crossings to major engineering feats spanning the full width of the canal channel, with clearance for 5,000-ton vessels passing beneath these. The Shaanxi Bridge is one of the most technically complex, a concrete-filled steel tube arch bridge whose main arch rib required precision fabrication and assembly in segments, with the final closure of the arch structure representing one of the most delicate construction operations on the entire project. The Zikai Bridge, whose opening in late April 2026 was one of the final milestones before navigation trials, required careful engineering to maintain both road traffic above and eventual canal traffic below. The Jinghaiwan Bridge, with all its arch ribs successfully closed in June 2025, spans one of the wider sections of the canal near the Bibu Gulf approach. Each of these bridges was not a separate project bolted onto the canal. Each was integrated into the engineering logic of the waterway, its height calculated to the centimeter, its foundations designed to withstand both the hydrostatic pressure of the water beneath and the dynamic loads of vehicles above, its design shaped by the same digital twin modeling system that governed every other element of the construction. 27 bridges, each one a precise component in a system that had to function as a whole. And then there was the water itself. Not the water that would eventually fill the canal and carry ships to the sea, the water that was already there. The rivers, streams, seasonal flood channels, and underground aquifers that had been flowing through this landscape for millennia. A canal does not arrive in an empty desert, it arrives in a living watershed. And every liter of water already moving through that system had to be accounted for, redirected, managed, or protected during years of construction, and then carefully integrated into the operational logic of the canal once it opened. Flood control was not a secondary concern. In southern China, the monsoon season is not a gentle inconvenience. It is a geological force. Guangxi receives enormous rainfall between April and September, and the rivers that flow through the province can rise meters in hours. The construction teams working in the Lingshan Basin in open excavated trenches up to 11 meters deep were working in terrain that flooded repeatedly during the construction period. Dewatering systems ran continuously. Drainage networks were constructed alongside the canal itself, not to serve the canal, but to protect the workers building it. Every pump mattered, every drain mattered, every temporary berm mattered, and while the monsoon rains came and the excavators kept working and the concrete kept pouring, another challenge was unfolding underground. The karst geology of Guangxi does not just make excavation difficult, it creates a specific hazard that canal engineers fear above almost all others: saltwater intrusion. When you connect an inland river system to the sea through an artificial channel, when you bridge the gap between fresh water and salt water, you create a hydraulic pathway. And if that pathway is not carefully designed, salt water from the sea can migrate inland through the canal, pushed by tidal forces and pressure gradients, contaminating freshwater rivers, agricultural irrigation systems, and drinking water sources upstream. This was not a theoretical risk. It was a known and serious engineering challenge that had to be addressed in the fundamental design of the canal, not patched after the fact, but built into the system from the beginning. The solution lies in the lock system itself. Each cascade hub, Madao, Qishi, Qingnian, acts not only as an elevation change mechanism for ships, but as a hydraulic barrier. When the lock gates are closed, they separate the water on either side. They prevent tidal salt water from migrating upstream. They maintain the freshwater character of the rivers connected to the Qi River system. The canal in this sense is not simply a channel, it is a controlled hydraulic environment, a system where water levels, water quality, and water flow are actively managed at every point along its 134-kilometer length. This management function, the ability to regulate water for agriculture, flood control, municipal supply, and ecological protection simultaneously with commercial navigation, is part of what makes the Pinglu Canal unlike the Suez Canal, unlike the Panama Canal, unlike almost any other major waterway in the world. Yan Cheng, the Director of Science and Technology Information at the Pinglu Canal Group, described it directly. Unlike those famous sea-level or near-sea-level canals, the Pinglu Canal is a modern multifunctional waterway that integrates navigation, flood control, water supply, irrigation, and ecological preservation into a single system. Constructing that kind of complexity under tight deadlines in challenging terrain with strict environmental constraints, he called a formidable engineering challenge. He was not exaggerating. Now let us go deeper. Because beneath the water, beneath the locks, beneath the bridges and the banks and the 27 crossings, there is an entire layer of infrastructure that no passing cargo ship will ever see. An invisible architecture, a system of systems that makes the visible canal possible. More than 10,000 temperature sensors embedded in the concrete of the lock structures, an intelligent temperature control system monitoring the thermal behavior of each concrete pour in real time, alerting engineers to thermal gradients that could cause cracking in structures designed to last for a century. Automatic concrete placing booms, pioneered on this project for use in river navigation hubs, allowing precise mechanized concrete placement in geometrically complex lock chambers where manual placement would be too slow and too inconsistent. BIM modeling, building information modeling, applied to the lock support columns with three-dimensional virtual models guiding the fabrication of customized formwork, ensuring that every pour matches the engineering specification to within millimeters. A satellite-based real-time construction progress monitoring system, updating the project's central command and control center continuously, allowing managers in Nanning to track excavation volumes, concrete pours, equipment deployments, and milestone completions across 134 kilometers of active construction simultaneously. A 72-hour water level prediction system, integrated with the hydrological monitoring network, giving engineers advance warning of flood events so that site protection measures could be activated before the water rose. An earthwork comprehensive utilization information management system, tracking every cubic meter of excavated material, routing it to its designated destination, ensuring that the 210 million cubic meters destined for gully filling and land reclamation arrived at the right location at the right time in the right condition for the land improvement work that would follow. Every sensor mattered, every data point mattered, every algorithm mattered. And then there were the fish. Guangxi's rivers are not just commercial waterways, they are ecosystems. The Xi River and its tributaries support hundreds of species of freshwater fish, including several that are rare, endemic, or commercially important to local fishing communities. A canal cutting across this watershed, excavating, redirecting, and permanently altering river channels poses an obvious and serious threat to aquatic biodiversity. Fish migration routes can be severed, spawning grounds can be destroyed, water temperature and chemistry can be altered. And if a canal locks up the connection between river and sea, migratory fish that move between fresh and salt water have nowhere to go. The engineering response to this was not token, it was structural. 36 ecological conservation zones were designed into the canal route from the beginning, not retrofitted after complaints, but integrated into the project's master plan before construction commenced. Wildlife corridors were built into the canal banks, allowing terrestrial animals to cross the waterway without encountering the navigation channel. Fish passage systems were installed at the navigation hubs, engineered pathways that allow fish to move upstream and downstream past the locks, bypassing the hydraulic barriers that would otherwise block their migration entirely. These fish passages are not primitive ramps. They are precision-engineered hydraulic structures, calibrated to the swimming capacity and behavioral patterns of the specific species that use them. At one of the hub fish passages, an AI-powered monitoring system was installed that can identify fish species from underwater imaging, count individuals passing through in real time, and track migration patterns continuously. Underwater lighting systems guide fish toward the passage entrance. Sonar detects movement and triggers alerts when unusual patterns suggest a problem with the passage function. By mid-2025, ultrasonic monitoring confirmed that fish had already resumed normal migration activities through the passage, a result that suggests the ecological engineering is working even before the canal has opened to commercial traffic. The canal is designed to achieve an ecological revetment rate of 86%, meaning that 86% of the canal's banks are stabilized using ecological rather than purely hard engineering methods, preserving vegetation, allowing natural bank processes to continue, and reducing the hard concrete edge that characterizes older canal designs. This is 36 percentage points higher than the Chinese industry standard for canal construction. The Pinglu Canal Group has described this as the nation's first carbon-neutral canal, a claim based on the combination of ecological design, low-emission water transport replacing high-emission road freight, and the land reclamation and reforestation programs along the route. Meanwhile, above the ground, alongside the canal banks, another transformation was quietly underway. Major industrial investment began flowing into the Guangxi corridor even before the canal opened. The logic was simple and powerful. Where a waterway goes, freight costs fall. Where freight costs fall, manufacturers follow. Boide New Materials launched a lithium carbonate production facility in Nanning with an annual capacity of 30,000 tons. Lithium carbonate is a critical material for electric vehicle battery production, and the ability to move it cheaply by water to ports with direct access to ASEAN markets is a significant competitive advantage. Sun Paper announced a 20 billion yuan investment in a fully integrated forest pulp paper industrial park along the canal corridor, a business that is deeply sensitive to transport costs and that will generate enormous volumes of bulk cargo for the waterway once it opens. These were not isolated investments. They were the early signals of what planners call a canal economic belt, the industrial clustering effect that follows navigable water, the same phenomenon that shaped the economies of the Rhine, the Mississippi, the Yangtze. Factories that want cheap bulk transport locate near canals. Canals that carry cheap bulk cargo attract more factories. The corridor becomes an economic axis, and the economic axis over time becomes a region. This is what the Pinglu Canal is designed to initiate, not just a shorter shipping route, an economic transformation. Now, by late 2025, the numbers told a story of a project racing toward its finish line. More than 97% of channel excavation was complete. An initial 18-kilometer stretch of the canal had already been filled with water, sitting full, quiet, reflecting the subtropical sky, waiting for ships. The 3 lock hubs were in final construction, their massive concrete chambers cured and tested, their gate systems installed and undergoing operational trials. Bank reinforcement had reached 80% completion. The 27 bridges were either complete or in final installation. Nearly 90% of the project's 72.7 billion yuan budget had been committed and spent. And across the project, something extraordinary had happened. Something that almost never happens in the world of major infrastructure. The project was tracking ahead of schedule. In a world where megaprojects routinely overrun their timelines by years and their budgets by billions, the Pinglu Canal, with its 315 million cubic meters of excavation, its 3 world-class lock systems, its 27 bridges, its 134 kilometers of karst and clay and river crossings, was on track to open for navigation in 2026 within the original projected window. By some reports, the first core waterway construction targets were completed ahead of their interim deadlines. Project manager Mo Rixung of CCCC Guangzhou Dredging. 35,000 workers, 3 years of continuous construction, over 300 million cubic meters of earth, and a project that did what very few projects of this scale ever managed to do. It held its line. Most cargo ships that will one day sail the Pinglu Canal will see only the water. They will see the banks sliding past, green and planted, the ecological revetment doing its quiet work. They will see the bridges overhead, 27 of them, each precisely cleared, each a different design, each carrying its road or rail load above while the ships pass through beneath. They will feel the locks, the slow rise or descent, the great gates opening, the water lifting them or lowering them from one level of the world to the next. They will not see the 10,000 temperature sensors embedded in the concrete around them. They will not see the 36 ecological conservation zones lining the banks. They will not see the 210 million cubic meters of earth that was excavated, transported, and transformed into nearly 1,000 hectares of new farmland. They will not see the karst rock formations that were mapped, blasted, and removed to make the path they are traveling. They will not see the hydrological engineers who calculated every flood scenario and built the drainage systems that kept the construction site functional through 3 monsoon seasons. They will not see the fish passage systems that are running quietly beneath the surface, guiding river species around the locks, so that the biology of the watershed continues to function even as the geology has been permanently rearranged. They will not see the AI monitoring system watching the fish. They will not see the satellite data updating the command center in real time. They will not see the digital twin, the virtual canal built-in software before it was built in Earth, that allowed engineers to test every failure mode before pouring a single cubic meter of concrete. They will not see the 35,000 workers who were here. They will not see the monsoon rains that flooded the trenches and were pumped out overnight so that work could resume at dawn. They will not see the karst voids that opened suddenly beneath the excavators and had to be filled and stabilized before the channel walls could be built. They will not see the blasting operations in the watershed crossing the 6.5 kilometers of hillside that had to be cut through to make the canal physically possible. They will see only the water moving south, carrying them to the sea. And that is exactly how it should be. Because the purpose of great engineering is not to show its own effort. It is to make something impossible feel inevitable, to make something that took years of human labor and ingenuity feel like it was always supposed to be there. The Pinglu Canal, when it opens, will feel like a river. It will feel natural. It will feel obvious. Ships from Nanning will sail to Qingzhou in hours instead of days. Cargo from Yunnan and Guizhou will reach Southeast Asian ports weeks faster than it did before. The 560-kilometer detour through Guangdong, the geographic inefficiency that shaped the economy of an entire region for generations, will simply cease to matter. Imagine it, a 5,000-ton cargo ship, 90 meters long, loaded with bauxite from a Guangxi mine or lithium carbonate from a Nanning processing plant, leaving the inland river system at Hangzhou, moving south, entering the canal, passing through the first lock at Qingnian, descending toward the intermediate level, moving further south through 134 kilometers of engineered landscape, ascending through Qishi, then Madao, the gates opening in 60 seconds, the ship rising 30 meters in a chamber the length of 3 football fields, then continuing south through the final stretch, past the 27th bridge, into the Qin River and out into the Beibu Gulf, into the open water, into the trade routes of Southeast Asia. The Pinglu Canal does not simply move cargo, it moves the meaning of geography. It says that a mountain is not a permanent obstacle, that a watershed divide is not a permanent wall, that the fact that rivers have flowed in one direction for 10,000 years does not mean they cannot be made to serve a different purpose for the next 10,000. Human engineering, at its most ambitious, does not accept the landscape as it is. It asks what the landscape could be, and then it moves 315 million cubic meters of earth until the answer becomes real. There is a figure that captures this project better than any other. One 5,000-ton cargo ship on the Pinglu Canal carries the equivalent load of approximately 100 railway wagons, a single ship, and at peak operational capacity, the 3 lock systems can process 6 of those ships every hour. 6 ships every hour, moving goods that would otherwise fill 600 railway wagons. Without the fuel of a road fleet, without the congestion of a rail network, without the 560-kilometer detour through Guangdong, water transport costs half as much as rail, 1/5 as much as road, 1/20th as much as air. And on the Pinglu Canal, that water transport will be available for the first time to the provinces of southwest China that have been paying the full road and rail premium for their entire economic history. The annual transport cost saving is projected at over 5.2 billion yuan, roughly $731 million, every year. That is not a projection built on optimism. It is a projection built on the difference between 560 kilometers and 0 kilometers, between the old detour and the new direct route, between geography as an obstacle and geography as an engineered advantage. When the first ships pass through the Pinglu Canal, when the gates open at Madao and the water carries the first commercial vessel from the inland rivers of southwest China to the Beibu Gulf, something will change in the economic geography of Asia. Not dramatically, not overnight, but permanently. The inland provinces that have always depended on their coastal neighbors for access to the sea will have their own door. The goods that have always traveled east before they could go south will travel south directly. The trade routes that have always been shaped by the natural flow of rivers will be reshaped by the deliberate decision of engineers to carve a new river where none existed before. This is what human civilization does when it is at its best. It does not accept the world as given. It looks at a mountain range between 2 river systems and asks, what if those 2 systems were connected? It looks at 65 meters of elevation change and asks, what if ships could climb that? It looks at 134 kilometers of karst rock, unstable soil, living rivers, and protected ecosystems and asks, what if we built something through all of that? Something that would still be here in 100 years, still carrying ships, still saving billions in transport costs, still creating farmland from excavated earth, still guiding fish through its passages. And what if we built it without destroying what was already there? The Pinglu Canal is the answer to that question. 65 meters, 3 locks, 27 bridges, 36 conservation zones, 315 million cubic meters of earth, 35,000 workers, 134 kilometers, and one door finally from the inland heart of southwest China to the sea. If you made it to the end of this video, thank you. This project deserved every minute of your attention. Subscribe to the channel if you want more stories like this, the engineering projects that quietly change the world, 1 cubic meter at a time. Leave a comment below. Which part of this canal surprised you the most? Was it the scale of the excavation, the water-saving locks, the fish passage systems? The fact that this is China's first river-to-sea canal in over 70 years? We read every comment, and we will see you in the next one.